In this lecture, we're going to talk about the properties of elastic collisions. Only this time we're going to talk about using the energy conservation and conservation momentum a little bit differently. And the first time we ended up canceling out the masses. But now what we're going to do is solve it a slightly different manner. And basically this is the result you get. If you solve for V1 prime, you end up with m1 minus m2 divided by m1 plus m2 times v1 plus 2m2 v2 divided by m1 plus m2. And so you can get the prime velocities here and here simply by solving the energy and momentum equation in terms of your initial conditions. Using these equations, we will predict the motion of the three specific cases, and we're going to relate them to observation. So what we're going to do is look at the two of the same mass particles colliding, a very heavy particle colliding with a very light particle at rest, and then a very light particle colliding head-on with a very heavy particle that's at rest. So for a collision of two particles of the same mass, where m1 equals m2, notice what happens. We get m minus m, which is 0. Okay? And then here we get m over, or 2m divided by 2m, and that tells us that v1 prime is equal to v2, because this term goes to 0, and this term here goes to 1. Same thing here. If we substitute in m, we get 2m down here, 2m up here. This is equal to 1. And here we end up with 0. So the whole term goes to 0. And we're left with v2 prime is equal to v1, which is what we have right here. Particles exchange velocities. A good example of this is playing billiards. The cue ball and the striped and solid balls are all the same mass. When the cue ball hits a solid ball, the cue ball stops and the solid ball takes off with the cue ball's velocity. Okay, so here you can see we have two particles with the same mass, two different velocities. They're going to exchange their velocities. Okay, so again, the particles exchange velocities. Another good example is found in nuclear reactor engineering. When uranium-235 fissions, it releases 3 high-speed neutrons. These neutrons are moving too fast to cause another uranium-235 nucleus to fission. So they have to be slowed down. What type of atom would be of most use here? So, when particles exchange velocities, an atom with a similar mass to neutrons would be a hydrogen atom. Hydrogen atoms are moving slower than the neutrons, and that would be great to help slow that down. The neutron would exchange velocities, slowing down while speeding up the hydrogen atom. Operational reactors use water for this purpose, heavier than hydrogen, but has many of the other benefits. So, for instance, you can also use the water for a coolant. Nuclear engineering, of course, though, is not as simple as that. There's a lot more involved in that process. So let's look at when we have a large mass striking a lighter mass at rest. For this case, we're going to assume that m1 is much larger than m2. And that means that m1 plus m2 is about equal to m1. And the same thing for m1 minus m2. It's about equal to m1. Then our equation simplifies to v1 prime equals v1 and v2 prime equals 2v1. And so basically what happens is m1 continues to have the same velocity, roughly, and this smaller mass goes off with a speed of 2v1. Now we have a larger mass striking a lighter mass at rest, same thing. The larger mass particle continues on its way with a slightly smaller velocity. The small particle moves at twice the initial speed of the large mass particle. Picture a bowling ball striking a beach ball at rest. That's kind of what's going to happen. Okay, so now let's look at a small ball striking a much heavier ball that's at rest. In this case, M1 is much, much smaller than M2. And that means that if I add M1 plus M2 or subtract M1 minus M2, I'm going to get about equal to M2. So looking at these equations here, we see that V1 prime is equal to negative V1, and that V2 prime kind of goes to 0. So here we have a very, very small massed object. It's going along, hits this big, huge particle at rest. The particle at rest kind of stays at rest, and the particle kind of bounces off and goes on in the opposite direction. Notice here we're saying roughly equal to. Okay, that does not mean it is equal to 0, but it's very, very small. The large mass particle remains mostly at rest. The small particle reverses direction with the same magnitude as its initial velocity. Picture a moving golf ball hitting a stationary bowling ball, or even a really fast ping pong ball hitting a bowling ball. Okay, so let's do some examples. A bowling ball has a velocity of plus v I hat when it collides with a ping pong ball that's at rest. The velocity of the bowling ball is virtually unaffected by the collision. What will be the speed of the ping pong ball? Pause the video now. Okay, let's see if you have the right answer. Let's go ahead and write in our velocities. V1 is equal to V, put 0 meters per second I hat. V1 prime is equal to plus V I hat. Actually, I don't need an I hat. Sorry about that. We got to get rid of that because I have a vector sign on the V. There we go. Okay, and so let's go ahead and substitute into our equation. We end up solving for V2 prime, and that gives us 2V. So the ping pong ball speed is twice that of the bowling ball. Oops. There we go. A baseball bat has a velocity of plus V I hat when it collides with a baseball that has a velocity of negative 2v I hat. The bat barely changes velocity during a collision. How fast is the baseball going after it hits? Okay, go ahead and pause the video and see if you can solve this one. Okay, so let's take a look at the answer. I'm going to go ahead and change this and put here, I'm going to put unit vectors on this side instead of vector signs. Okay, so here's what we have. We're solving for V2. Using our equation, V1 minus V2 is equal to negative V1 prime minus V2 prime. Solving for V2 prime. Substituting in our numbers. We get V I hat plus V I hat minus negative 2V I hat. And that's going to give us V2 prime is equal to 4V I hat. Okay, let's go ahead and do another example. Two objects with identical masses have an elastic collision. The initial velocity of M1 is 6 meters per second I hat, and M2 is negative 3 meters per second I hat. What is the velocity of M1 after the collision? Go ahead and pause the video now and see if you can solve this. Okay, let's take a look and see. I'm going to go ahead and change this and put my vector signs on here because they're vector quantity, and I'm going to give it direction. Okay, so when the identical mass objects experience an elastic collision, they swap their velocities. So V1 prime is equal to V2, which is equal to negative 3 meters per second. V2 prime is equal to V1, and that's equal to 6 meters per second I hat. So the velocity of M2 must be negative 3 meters per second I hat. Okay, I have skipped the previous problem. Let's go ahead and look at number 43. A golf ball is hit against the solid cement wall and experiences an elastic collision. The golf ball strikes the wall with a velocity of 35 meters per second. I had. What velocity does it rebound with? Go ahead and pause the video and see if you can solve this one. Okay, let's take a look and see if you got the right answer. When a light object strikes a very massive object, the light object rebounds with the opposite velocity, and in this case, it's going to be negative 35 meters per second I had. See, you didn't even need a formula for this one. Okay, in the next video, we're going to talk about collisions in 2 dimensions.